Looking out the window at a scene like this, a passenger sees a serene, white landscape of clouds, but a pilot knows that this exact layer of moisture can behave like a minefield. The threat comes from supercooled droplets. This is liquid water that remains in a fluid state far below the freezing point of 0 degrees Celsius. The upper atmosphere is often too clean for its own good. Without microscopic dust or impurities, called freezing nuclei, the water has nothing to latch onto to form an ice crystal, allowing it to stay liquid down to -40 degrees. A fast-moving aircraft provides the physical trigger. When this supercooled liquid slams into the cold metal skin, the kinetic impact provides the energy required for the water to freeze instantly on contact. Flying into these temperature bands means navigating a landscape where the air itself is waiting to react to the airplane's presence. To find where this threat hides, look at the macro weather level. As air rises, it expands and cools, condensing into visible clouds. The speed of cooling and strength of updrafts dictate whether it falls as common rain or the dangerous supercooled variety. From inside the cockpit, a pilot watches for the moment ice pellets begin to drum against the windshield. This sound acts as a profile of the air layers sitting directly above the plane. Encountering these frozen pellets indicates that a layer of warm rain is falling through a sub-freezing band. It is a warning that a layer of severe freezing rain is accumulating just a few hundred feet higher. Survival depends on reverse engineering these environmental symptoms, because the most dangerous conditions are often invisible until the airframe begins to change shape. When supercooled droplets strike the airframe, the outside air temperature determines the physical structure of the ice that forms. At temperatures below -15 degrees Celsius, small droplets freeze the millisecond they make contact, forming what pilots call rime ice. Freezing instantly, rime ice traps microscopic pockets of air. This creates an opaque, brittle buildup that clusters along the leading edges of the wings. In slightly warmer conditions, between 0 and -10 degrees, the moisture forms a much more resilient, clear ice. This is typically found in moisture-heavy cumulus clouds. These larger droplets freeze slowly. Instead of shattering, the liquid flows backward over the wing's surface before finally solidifying. The result is a dense, transparent sheet that embeds itself into the aircraft's skin. This smooth layer is incredibly difficult for standard de-icing boots to crack and remove. A shift of just a few degrees determines whether the ice is a brittle frost or a heavy, transparent shell gripping the airframe. There is a common assumption that ice brings down airplanes simply by making them too heavy to stay in the air. In reality, the threat is geometric. Ice destroys the precise shape required for flight. Lift is generated primarily on the first 25% of a wing's leading edge. This is the exact zone where ice prefers to accumulate. Even a thin, rough layer here disrupts the laminar airflow. The air separates from the wing's surface and becomes chaotic, no longer providing the pressure differential needed for lift. This disruption can instantly reduce an aircraft's lift by 30%, while parasitic drag can increase by as much as 200%. Structural ice turns the physics of the wing against itself, causing stall speeds to rise far beyond the pilot's expectations. This loss of lift initiates a cascade of failures across the entire aircraft. In severe conditions, roll upset can occur. Airflow separation over the iced wings creates self-deflecting forces on the ailerons, causing the plane to roll violently without any pilot input. Then there is the matter of pitch. Most aircraft are designed with a center of gravity that naturally wants to pull the nose down. To fly level, the horizontal tail must constantly push downward to hold the nose up. The tailplane is significantly thinner than the main wing. This profile makes it a highly efficient collector of ice, allowing it to choke with frozen accretion much faster than the rest of the plane. When a pilot deploys wing flaps for landing, the redirected airflow can suddenly stall that iced-over tail. The tail's downward force disappears, and the airplane's nose snaps into a vertical nosedive. Structural icing is an unauthorized mid-air redesign of the aircraft. To survive, pilots must respect the sky as a dynamic physical fluid, capable of rewriting the laws of aerodynamics in seconds.